Okay, Assalamualaikum warahmatullahi wabarakatuh. So today we are going to discuss about the topic linear least squares data fitting or least square fitting. So here we are given a data and we need to fit this data into some function. From here we propose the function is a linear function. It is considered as polynomial also, where the degree is equal to 1. We can visualize it this way. Say that we have data. This is the sample data. Say that x is equal to 1, 2, 3, 4, 5, and so on. So we have, okay, I just randomly put the data, plotting the data based on this table 8.1. So let's say we want to fit it inside this what we call as straight line polynomial degree 1, or straight line. Of course, it is, if we draw the graph, it will produce a straight line. So for this one, we want to minimize the error. Error here means from this point to our line here, what is the difference? And from this, what is the difference from here? And also for each point, what is the difference of the polynomial with degree 1 with the data provided? So this is what it means. Since we have 10 data, so here we sum until equal to 10. Okay, if you are not familiar with this sum notation, you can also write here, write it like this. y1 minus, this is from the data, and let's say from the polynomial, let's say p1, and then you square, then you plus y1 minus p2, then you square, then you do this until, this one is y2, y10 minus p10 square. Yes, you can also write it in this way. And of course, since I use p here to differentiate with this y. Okay, and to do this, we see here we don't know the coefficient. The problem here, we propose it is a polynomial with degree 1, but then we don't know the coefficient. So what value should we put here as a coefficient? So to do this, we must minimize the error, so that with respect to A1 and A2, minimize the error here means we want to, the difference here, we want to minimize the difference between these two. Okay, and I clearly write here, it is clearly stated over here, minimize the error, differentiate with respect to A1 and A2, because this one is what we want to, the only value that we can control. Means we cannot differentiate with respect to y or x, because the data is fixed. It is already there. We cannot simply manipulate the data based on our preferences. Okay, then of course we learn from calculus, if we want to minimize something, then derivative will be equal to 0. I think if we learn, our basic calculus is very good, then we will no problem. We got no problem to understand this. Okay, so first we have to compute this and this, and equating the derivative equal to 0. You use partial derivative instead of dE here because we have got so many variable here. So it is wise to use this notation instead of D. Okay, so here we take this one is E. We take E here. Yes, it is clearly stated here. M will be equal to okay, we cannot use 10 here. We will just use a variable, some variable M, because we want to find this general formula. So instead of using 10, we put variable M to generalize the formula. And here we differentiate this. Of course, this is DE. DE here is equal to this, and we do we differentiate these terms, these whole terms. We get this. Say this power, we bring it in front, and then we differentiate whatever inside. Differentiate with respect to A naught. We'll take the coefficient of A naught over here. That's result in -1 right over here. And similarly, this derivative over here, we take we differentiate, we take the partial derivative with respect to A1. We treat the other terms as a constant, and we see here we these two power bearing in front, and then power -1. Power -1, 2 minus 1 is equal to 1. So therefore, it is power equal to 1 in this term. And these two, because of this power 2 over here. And then inside, since since A1, we differentiate with respect to A1. A1 is power 1. Therefore, we just simply take the coefficient. The coefficient is negative xi, which result in negative xi over here. And then after that, we just use algebraic manipulation. This whole thing equal to 0. Maybe I should write it this way. So we divide this side and this side equal to, we divide with 2, means this one cancel, this one, divide both sides with 2, and then we also divide with -1, and then by algebraic manipulation we got these terms over here. Okay, maybe you are not very clear. Maybe I should write something. So as we know, after we doing that, this one cancel, this one also got no more, and we can, you know, expand. We can write it this way. This sum, we bring it inside A1 xi. We put sum like this, m, since the letter m is used here, so I will use the same variable. Wait, this one is equal to 1. We need to follow all of this. You just put this sum inside. That's it, nothing else. Okay, and then of course this one is A naught minus like this. So then we equate this equal to 0. We bring this term to there, so we got this value. We got these terms. It's resulting in this expression, in this equation. And then similarly, this one also we did the same thing. And by algebraic manipulation, we got this whole term right over here. For A naught, it can be expressed in this way, and A1 can be expressed in this way. And of course, this here, we also can use what we call as Gaussian elimination with like this matrix. but since it is degree 1, it is quite simple, and we can express it in this form straight away. Okay, and so this one is the table from here, 8.1. So we calculate the value of this sum, this sum, this sum, this sum, and the whole sum. We have to compute it accordingly. Okay, and here we just substitute the value 385 is equal to summation of x squared from 1 xi from I equal to 1 to I equal to m, and that one is here, yes, summation of x squared. So we put this value inside here. Okay, means we take these things, we square, and then for every square we sum up all of them, resulting in 385 here. Then we simply substitute the value into our formula, our equation here, and then after that we calculate this sum the same way. This one we sum up all of this and take this value, we substitute here, resulting in 81 over here. So you do this accordingly, and you will get the coefficient for our polynomial, which is a0 equal to negative 0.360 and a1 is equal to 1.538. And also we also calculate the error here, which is equal to 2.34, and this is the result. We have y is equal to a naught plus, this one is naught, plus a1x. Okay, so ax, the coefficient of x is 1.38, a 1.538, so we put it here, and a naught is equal to this, so we just simply put it over here this way. And and this is for polynomial degree 1, or we call it as linear. But when it is polynomial with higher degrees, then it is not that easy, because say that these are the data. We can take degree 2, means it is parabola, or it is cubic function, quartic function, or quintic. Then it is not so easy to compute. Means we have to do it this way. I'll explain it here. Okay, same things over here. We calculate the error. So the error here, we take this polynomial, we take the difference of this polynomial and we square. The only reason why we square is just to get rid of negative value. Let's say we got something like this. Yi minus this might result in a negative value, because let's say like this. Let's say yeah, like this. So this one, the value of y, the point is below our polynomial, so this result in this value is greater than this, so it will produce negative value. So to avoid that things to happen, we square. Actually we can use absolute value. We use modulus, but it is the reason we use square instead of what we call as absolute or modulus is because modulus is very hard to compute algebraically, very hard to manipulate it algebraically. Okay, and then we minimize the error. The same idea, we equate every coefficient every derivative of the every error with respect to the coefficient equal to 0 here. Okay, and here we take dA naught is equal to this expression. Okay, means same idea. We bring this one in front, and then we will have negative value. Say that this one is equal to this. Say that we have 2a like this. Wait, yeah, and then of course when we differentiate this value with respect to a, I think no need 2 over here, no need 2 here, and then yeah, like this is enough. With respect, maybe use b, yeah, like this. Okay, so we differentiate this, we will get we bring the power in front, and this one we minus 1. Of course this one is still the same, and we differentiate this value inside with respect to a. We got, just simply take the coefficient, but here the same thing. That's why we got the negative 1 over here. Actually we need to put negative 1 like this, but it is easier if we put it in front like that. So that is why there is negative 2 here. Similarly, this one we differentiate with respect to a1. When we differentiate with respect to a1 from here, this one we differentiate with respect to a1, we bring power in front, resulting in this 2, and we copy the whole term, and we take the coefficient of a1, which is negative x1 xi, because I is equal to 1, so negative x, we take negative x. That's why I got negative and x over here. So the whole way until we get until ak. This is just the generalization. Okay, and then after that, this lead to this equation, and this is what we want. This can be solved using matrix, or what we call a system of linear equation. So we can use whatever method that we have learned before, which are Gaussian elimination or Gaussian-Jordan elimination, and also maybe LU factorization, and any method that we know. Yeah, so here is some example. Okay, some example. So we have some data over here. We need to fit this data inside the quadratic function. Yes, quadratic function, because we have, this is from the textbook. I took it from the textbook and put it here just for better understanding. Okay, and then we take this thing, we see over here we have a1, a naught, n. So just a naught n, we just calculate the value of n over here. Okay, the value of n is just how many terms are there. Actually, this is actually xi power 0. We calculate it like that, a1 power 0, which means every term with power 0 will be equal to 1. So that's why we got this value with power 0, then we equal to 1. Then we'll get 1. Then these terms also 0.25 power 0 will be equal to 1. Then we submit all, since it is all equal to, we power all of them equal to power equal to 0. Therefore all will be equal to 1. Then 1 plus 1 plus 1 plus 1 5 times will result in 5 here. And similarly, this 2.5 here is originated from the summation of the term. So 0, 0 plus 0.25, 0.50, 0.75 plus 1 will have this value. And you need to calculate the sum. Here the sum, this one, and AK we take 2. Since what we want to calculate is what the polynomial that we want to fit is the polynomial degree power of 2, so we equate k equal to 2 here. Okay, and then after we do the sum, we need to find this value over here. Find this value. Yes, and that's why we got this system of linear equation. And of course we can use knowledge from linear algebra to compute the value of a0, a1 and a2, which are the coefficients of our polynomial degree 2. So this is the result when we solve the system. Okay, and then after we calculate the coefficient, we substitute it inside our polynomial. That will result in this function. So this is our polynomial degree 2 with the coefficient that we have compute before. You just simply substitute all the value inside. Okay, and that's it. That is the way we find the suitable polynomial to fit with our data, with the given data. Okay, and for the error computation here, we do the same. We simply substitute xi inside the polynomial and will result in this value. Okay, means we calculate let's say the given data is 0, 1, means the point is 0, 1. This is from the data. This xi and yi is from the data, and this one we simply substitute this value of x inside here. So we substitute 0, means this one cancel, will result in 1.0051, which we have here. Okay, and then this one similarly we substitute the x into with this x, and we got p2x equal to this one. And we do for all of the other 3 value here, and then we calculate the difference of this yi, which is given which is from our data provided, and then we find the difference between the given data and our proposed polynomial. Okay, and we sum it all. Use this one and then we sum up like this, resulting in this value. Okay, that's how we calculate the error. And at times it is appropriate to assume that the data are exponentially related. Means we can also represent our fitting with instead of polynomial, we can fit it with exponential function also. Of course, we use different approach. If we use the first method that we have used like before, we will have a non-linear system of equation, which is very, very complicated. So we manipulate this. This is our proposed function that we want to fit. So we manipulate it algebraically, resulting in this expression, in this equation like here. And then we take this value, we equate it with linear. This one is linear because we see here x is power equal to 1. The highest degree of x is equal to 1. So it is a linear function. It is known as polynomial degree 1. So we just only need to take this term. Wait. Maybe use highlighter here, and equal to here, equal to this, and this one equal to this. Yes, and m will be equal to whatever data that we have. Yes, this is just for generalization. And then we see m here, a naught m, because power equal to power, anything power 0 will be equal to 1. Therefore 1 plus 1 plus 1 plus 1 plus 1, and we have m times 1. That's why we have m over here. Okay, and similarly the same process will result in this sum. Okay, and then this is just like what we have discussed at the very beginning. This one we have discussed this, how to calculate the how to compute the coefficient. Okay, a0 and a1, and then this is again from the data provided. Yes, the same thing. Just we take the polynomial, and the only difference is this one, this b here. Instead of using b we take maybe a equal to a0, and in this case a1 is equal to ln b. And then when we want to find b, we neutralize the ln with exponent, and we then result in this value here, and then we substitute again inside our polynomial. So this is the result. This is our exponential function, and and then we plot the graph. It is displayed right here, and calculate the error. The textbook use absolute value, but normally we will use exponent. So we just calculate the sum of this all. We just plus all of this value here, this one plus this one plus this one plus this one plus this one, then we will get the total error. And I think that's all from me. If you have a question, you may ask in the comment section below, or just simply we may have another discussion later on, inshallah.